Let's consider the one-dimensional motion of a particle which is attracted to a fixed center by a force proportional to its displacement. The body feels a potential of this form. This description is very important because either in classical and quantum mechanics, the harmonic oscillator can approximate a lot of potential. In fact, using a second-order series expansion around the minimum of a certain potential that depend only on the displacement R, we found exactly the form of harmonic oscillator. We are going to solve the Schrödinger equation using this potential. What we will find is the wave function, which modulus squared describes the probability density to find particle in a certain position inside the potential. What we will see is that commutation relations induce a quantization in energy, and of course the wave function will depend on a certain integer number n. And comparing the probability density, we see that for small n, the classical and the quantized theory are very different, but for increasing n, the two theories have to match. A fancy effect that appears only in quantum theory is the tunneling effect. Classically, a particle remains trapped inside the potential unless it has energy greater than the potential wall. In quantum physics, it can overcome the potential barrier also if it has less energy than the required. This is possible thanks to the Heisenberg uncertainty principle. When the particle approaches the wall, we are measuring its position accurately. This gives an high uncertainty in the momentum, so we have great uncertainty in energy. This uncertainty gives to the particle non-zero probability to overcome the wall.
Hello everybody, today I would like to open this channel introducing the harmonic quantum oscillator. My aim is not to be too rigorous but to focus on the physical meaning of our calculation. So let's start from the classical Hamiltonian. Now, in principle, we could resolve the eigenvalue and eigenvector equation for H, but we could approach a simplest calculation using the algebraic method of Dirac that consists in defining two operators called A and A DAG. Why introducing this operator will be clear doing a DAG A. Remember that X and P, they don't commute in general because they are operators. The commutator is equal EH bar. So putting 1/2 in the other side and multiplying everything by omega H bar, we have rewritten the Hamiltonian in terms of a DAG and A.
Calling a DAG A operator n, we are going to find the eigenvalue and the eigenvectors of n.
We have also the eigenvalue and the eigenvector of H, because H and N commute. This is trivial, and so we can use a common base to describe the two systems.
And also the eigenvalues of H, the energy values are trivial to find.
Before proceeding, we give some commutation relations between A and A DAG. This can be calculated just expressing the explicit form of A and A DAG. We are going to see that A and A DAG are the elevators operators for n. In fact, the commutator with these operators gives less A for the descendant operator A and the plus A DAG for the ascendant operator A DAG. So as said before, we are going to find the eigenvectors for the operator n. To see this, let's calculate the operator n applied on the state made by the product of A with n. We have found that an is eigenfunction of n with eigenvalue n less 1. So we can interpret an as the state n less 1, and clearly A applied on n will be proportional to n less 1. In the same way, a dag n is proportional to n plus 1. So with this definition, we can use the operator a that decreases the principal number of the state n by 1 and a dag that increase this by 1. So finding one state, we can reach all the others using a and a dag. But let's see if there are upper or lower limit. For this, let's calculate the modulo of the state, but this is the number operator. Choosing the eigenvectors normalized, we have this scalar product is surely greater or equal to 0. So we can assert that n is greater or equal to 0. So there will be a lower limit at least 0. Let's see that 0 is inside our domain in such a way that if we take the lower state that we call with 0 and we apply the operator a, we surely have 0 because we are going to lower the state n by 1, but we have already the lower state. Therefore, applying a dag to the previous state, surely we have again 0. But this is n applied on 0, that is 0. So 0 is taken. But if 0 is the minimum and we can increase and decrease by 1, we can only have n belonging to 0, 1, 2, and everything. Before proceeding, let's just demonstrating that there is no upper limit. A dag on max, we should have 0. But calculating the modulus this using the first relation above, and this is of course 1 because the eigenvectors are normalized, that is not equal to 0. Let's just underline that n can be only natural because if n was another number, we could apply several times a and couldn't reach the minimum. So to conclude the discussion on eigenvectors n, let's calculate the normalization of the operators a and a dag. So we have c1 modulus squared equal to n, that gives unless of a phase, a general phase, we have c1 equal to square root of n.
And in the same way we can find normalization for a dag,
leading to unless of a complex phase, giving square root of 1 plus n. So c1 and c2 are the right eigenvalue for the operator a and a dag.
Therefore, in principle, using the operator a dag, we could reach every state n using recursively a dag.
So in general, n can be written as a dag applied n times on the ket 0 divided by factorial n on the square root.
Now to find the wave functions, we could proceed in such called the analytic method that consists in applying the operator a on the ground state that gives 0.
But now multiplying by the brakes, expliciting the operator a, that is this bad guy, we have 0 again. No jokes. And then remembering that p can be written as x and p are both operators of x. When the brakes act on them, they leaves the eigenvalue. We can explicitate the wave function, and these are no longer operator, but this is the wave function of n equals 0 and function of the position x. Now, throwing away the normalization, we are left with the first order differential equation that is, of course, have the solution phi 0 of x. To find n, let's see how to normalize this guy. We want that the phi star phi is equal to 1, that is a Gaussian with solution n modulus squared square root of h bar pi over m omega, imposing that this is equal to 1. We have
n. Finally, the solution can be written as follow, and it's possible to write it as wave function phi 0 of x and as a scalar product of x and agent state. To find the wave function with n greater than 0, we just apply the operator a dag n times.
Before proceeding, let's just introduce change of variable. Let's call x position operator over x0. So with this definition, we can rewrite a and a dag with a clear fluidity that is as follow. With this redefinition, the question above, it's simpler. Just to conclude, let's see what happens when we apply one time the differential operator. At the end, we have a polynomial that we are going to call h of degree n and variable c. So finally, let's write
the more general expression for the wave function. With this equation, in principle, we could achieve any wave function.